So in this section, what we're going to be talking about are essentially the factors that affect the position of our equilibrium. So what we discussed in the previous section was essentially that we said, okay, well, most equilibriums are dynamic equilibriums, meaning that there is a forward reaction and then there is a reverse reaction, and the rates of both these forward and reverse reactions are equal, such that there's no change in concentration, right? So that was a dynamic equilibrium, and we said, okay, dynamic equilibriums can only occur in a closed system, which is essentially that the reaction or the system has no influence from the surrounding environment. So that's what we said had to occur with a dynamic equilibrium. Now, what we're going to focus on in this section is looking at, well, what happens if we temporarily open up that dynamic system to the environment? So we temporarily go from a closed system to an open system. What happens to equilibrium then? Okay, and the main principle that governs this whole section is essentially known as Le Chatelier's principle. And what Le Chatelier's principle says is that if a system at equilibrium is disturbed, so the system is already at equilibrium, what happens when we disturb that system? Then the system will adjust itself to minimize that disturbance or oppose the change. So what that could mean is, okay, we have a dynamic equilibrium, it's a closed system, we let it reach equilibrium, right? Then what happens if we introduce a disturbance to that system? For example, maybe we add in more gas or we change the total pressure of the system. What if we add in more concentration of reactants, right? Or what if we dilute the system? What happens then, right? What if we change the temperature, or we heat it up, or we cool it down? What happens then? And what Le Chatelier's principle says is that for any of these changes, the system will adjust itself to minimize that disturbance or to oppose that change. Not completely get rid of that change, but just to minimize it, okay? And the analogy I like to use sort of with Le Chatelier's principle, which we'll talk about throughout this section, is try to think of it as like you're standing outside in a hot day, right? So normally it's a pretty cool day, and then suddenly it gets really, really hot. So essentially the increase in heat is disturbing your system, right? It's disturbed you. So what do you do to minimize that heat increase? Well, you might move to the shade, or you might put a hat on, or you might eat an ice cream or something like that, right? So if a system is at equilibrium and you disturb it, it will adjust itself to minimize that disturbance. Not completely get rid of the disturbance, but minimize that disturbance. And we're going to be looking at sort of that principle throughout this section, okay? Now, let's just jump straight into an example, because that's probably the easiest way to understand how all this equilibrium stuff and Le Chatelier's principle work, right? So the first example that we're going to look at is combining carbon dioxide and also water to form this molecule here, which we call carbonic acid, okay? So the equation for a reaction like this is H2O, which is a liquid, reacting with CO2, which is a gas, to go to form carbonic acid, which is H2CO3, and we write that as aqueous. And this is actually an equation that you might not necessarily have known existed, but you see all the time, and this is actually an equation in soft drink, and we'll talk about that, how that works in a sec, okay? And the delta H for this reaction here is negative. And what that essentially means is that, well, a negative delta H, that's an exothermic reaction, right? So it releases energy or releases heat. So the forward reaction, right, releases heat, right? And we know this is a reversible reaction because we see sort of this city rail sign here. We know it's sort of a reversible reaction, meaning that we have water reacting with carbon dioxide to form carbonic acid, right? And a bit of heat, right? But then we also have carbonic acid breaking down and absorbing some of that heat to form carbon dioxide and water, right? So that's essentially what we mean when we said an equilibrium reaction in the previous section, right? You have your reactants going to form your products, but then your products are also breaking down to form your reactants, right? And the delta H is to describe the enthalpy change for the forward reaction, okay? Now let's have a look at some of these factors and see how, maybe changing temperature might affect equilibrium. But first of all, before we do that, we've got to assume that the system is already at equilibrium, right? So assume system is already at equilibrium, right? So we're assuming that the system is already at equilibrium. And why do we have to do that? Well, if we go back up here and we looked at Le Chatelier's principle, it says that if a system is at equilibrium, so the system has to first be at equilibrium, then we disturb it, and then we see what happens, right? So the system at the start has to be at equilibrium, right? So that's why we're assuming it's already at equilibrium. So assuming the system's at equilibrium, what happens if we change the temperature? So let's first go with an increase in temperature, and we'll do it in pink, so it sort of reflects an increase in temperature where things are getting hotter, right? So what happens when we increase the temperature? Well, Le Chatelier's principle said that no matter what, if a system is at equilibrium, which we assumed it was, right? If you disturb it, so the disturbance is the temperature increase, it will shift the position of the equilibrium to minimize that disturbance, all right, or oppose that change. So what's essentially happened here? We've increased the temperature. And by Le Chatelier's principle, the equilibrium will want to then decrease that temperature a little bit, right? Because it's like, it's getting hot and then you want to move into the shade. So it wants to decrease that temperature a little bit. So how does it do that? Well, we can look at this sort of heat here, right? And so if we increase the temperature, what that system's going to want to do is this carbonic acid is going to want to absorb some of that heat, right? And then convert it back to CO2 and H2O, right? This carbonic acid is going to break down to form CO2 and H2O, right? Because in doing so, it's going to absorb some of that heat. Right, so we increase the temperature of the system. It doesn't like it, so then the product side, the carbonic acid, it is going to absorb some of that heat and then move back towards the reverse direction, or in the reverse reaction. Right, so what we say is if you increase the temperature, the equilibrium will shift to the left. Right, so it will shift to the left via Le Chatelier's principle. Right, via Le Chatelier's principle. Right, and I'm going to write Le Chatelier's principle from now on as LCP. Never do that in an exam, never abbreviate it. But just for the sake of time, I'm going to write it as LCP from now on. Right, but it's going to move to the left via Le Chatelier's principle to minimize the heat increase. Right, to minimize the heat increase. Okay, so it's going to move to the left to minimize that heat increase. Right, and why does it do that? Why does it shift to the left? It's because the carbonic acid, by breaking down to form carbon dioxide and water, it will absorb some of that heat, because the reverse direction is an endothermic reaction. It's going to absorb energy, or it's going to absorb some of that heat, and that will help minimize the temperature a little bit. Okay? Now, contrastingly, if we decrease the temperature, right, we cool the system down, what will happen? Well, by Le Chatelier's principle, you want to heat it up a bit. Right, so how does it heat it up a bit? Well, it takes some of these reactants and then converts it to the product, because by converting to the product, you're going to release some heat, and by releasing heat, that's going to heat up the system again, right? So the equilibrium will shift to the right, okay? The equilibrium is going to shift to the right, because like we said, the reactants, when the reactants mix together and then go to form our product, it's going to release heat, and that's going to minimize this initial temperature decrease by increasing the temperature a little bit. So what will happen in this case is you're going to have less reactants, because the reactants are going to convert themselves to the product to form carbonic acid. So you're going to have less reactant and more product, okay? Less reactant and more product. And then in our previous example, if we increase the heat, all right, you're going to have some of the product converting to form our reactants. We're going to get more water and more carbon dioxide, and then less carbonic acid. So if we increase the temperature, we're going to get more of our reactants, less of our products. If we decrease the temperature, the equilibrium is going to shift to the right. So we're going to get less of our reactants. That's all going to get converted to our product. So we're going to have more product, less reactant. Okay. Now, so that's temperature. Now we're going to talk about carbon dioxide or gases in general, right? Increasing the amount of gas. And when we increase the amount of gas, we say that's increasing the partial pressure of CO2, okay? So when we say increasing the pressure of gas, that's increasing essentially the partial pressure, okay? So partial pressure of the gas, which was CO2 in this case, right? Because you're just adding in more CO2. You're not changing the pressure of the entire system, which we'll look at in a sec. You're just changing the pressure of CO2. So it's adding in more CO2, increasing the partial pressure of CO2. You can think of it almost like increasing the concentration of CO2, but we generally don't use concentration when we're referring to gases. We just say the partial pressure, but they mean the same thing. So we're increasing the amount of CO2. Now, if you have a look at this equation here, if I increase the amount of CO2, so if that goes up, right, the equilibrium is going to want to shift to the right in order to minimize some of that CO2. So if I increase it, right, what's going to happen is if I just copy that equation down again, just to illustrate that point, if we say, for example, we increase the amount of CO2 initially, that's going to disturb the system. The system doesn't like it. So how does it get rid of some of that CO2? Well, it's going to shift to the right, because what that's going to do is going to take the water and take some of that excess CO2 and convert it to carbonic acid. So over time, the amount of CO2 is going to decrease, right? So what we say is therefore the equilibrium will shift to the right. Okay, the equilibrium will shift to the right, or in other words, it's going to favor the forward reaction. Okay, it's going to favor the forward reaction. Right. So if we sort of map out what happens, and we'll look at sort of reflecting these changes in equilibrium on a graph in our next example. But essentially, if we just briefly map out what happens to the CO2, well, the amount of CO2, if I just draw the graph like so, right, and if this is concentration over time, right. And we'll talk more about sort of what the labels are and stuff in our next example. But what happens with CO2 is it's kind of chilling along, right? It's not changing because it's at equilibrium. We assumed it was at equilibrium. It's kind of chilling along, and then suddenly someone dumped heaps of CO2 into the system. So what happens when someone dumps heaps of CO2 in the system? That's going to spike the concentration of CO2, because this is CO2, right? The concentration of CO2 is going to spike up, right? Because I was just dumped a whole load of CO2 in the system. Now the equilibrium doesn't like it, and so what that's going to do, it's going to shift to the right. So it's going to take some of that water, take some of that CO2, and produce carbonic acid. So what's going to happen to the amount of CO2 over time? Well, then it's going to start to slowly decrease until it reaches a new equilibrium. Right? So it's going to slightly decrease until it reaches a new equilibrium. And hopefully you notice you don't go back to the original amount, right? That's not the purpose of Le Chatelier's principle. That's not the purpose of shifting the equilibrium. It's not so we get back to our original amount. It's just so we minimize that disturbance a little bit. And then it's going to sort of compromise and then establish a new sort of equilibrium, like so, okay? So that's how pressure, or partial pressure more specifically, can influence the position of the equilibrium. So if I increase the partial pressure of the CO2, it's going to shift it to the right. And then in reverse, if I decrease the partial pressure of CO2, it's going to shift it to the left. So if I have less CO2 or take CO2 out of the system, it's going to want to make up for that. So it's going to take some of this carbonic acid, break it down to form CO2 and H2O to make up for that. Okay? So that's partial pressure of CO2. And then the final thing that can affect the equilibrium is changing the total pressure, okay? So changing the total pressure. And let's just say we increase the total pressure. And if we think back to year 11, it's probably sort of deep into the memory. But to increase the total pressure, the most common thing that we do is decrease the volume, right? So to increase the total pressure, or to change total pressure, we generally change volume. So let's just explore what happens when we increase the total pressure. When we increase the total pressure, so not just by adding in more of one particular gas, but we might add in more of all the gases, or in this case, we might decrease the volume. So let's just say what happens when we decrease the volume. Well, we know that decreasing the volume increases the total pressure of Boyle's law back in year 11, but sort of intuitively, why does that occur? Well, if I've got a system like that, and let's just say I've got my 4 particles of gas like so, and then I sort of severely decrease the volume, I still have my 4 particles of gas, but now they're sort of so tightly packed together, the pressure is going to increase, right? So therefore the pressure increases, right? If we decrease the volume, right? That's essentially what's going on, right? Now, the idea with changing the total pressure is that it's a little bit different to partial pressure now. The idea is that when we change the total pressure, the system will want to shift to the side with less moles of gas. So that's sort of a key takeaway. If you change the total pressure of the system, it wants to shift to the side with less moles of gas, okay? And then obviously that's the opposite. If you decrease the pressure or increase the volume, we'll talk about that in a sec. But you want to shift to the side with less moles of gas. So now if I draw the equation again, right? So if I write it out again, H2O plus CO2, and I'm just going to make it clear that the CO2 is the gas, right? And that's going to go H2CO3 aqueous, like so, and then water's liquid, right? So what's going to happen is if I change the total pressure and I increase the total pressure, again, the system's not comfortable, it's not happy, so it wants to decrease that pressure. How's it going to decrease that pressure? Well, it's going to shift to the side with less moles of gas. In this example here, which side has less moles of gas? Well, on this left-hand side, there is 1 mole of gas, it's the CO2, and on the right-hand side, well, there's no moles of gas because the carbonic acid is aqueous. So in this example, right, the equilibrium will shift to the right, okay? Will shift to the right, okay? Right, because there's less moles of gas on the product side, okay? Less moles of gas on the product side, okay? There's less moles of gas on the product side, right? See, there's no moles of gas on the product side. And how does this sort of help the system? Well, what we're essentially doing is we're taking that excess gas, right, and then we're shifting it, like, because so we've increased the total pressure in the system, so we need to decrease the pressure again. So how do we do that? We want less gas present, because if we convert it out to like liquid, solids, or aqueous, there's no longer gas exerting pressure on the system, so it's going to shift to the side with less moles of gas, and in this case, it shifts it to the right-hand side, okay, because the product side has less moles of gas. It might not always be the case, right, but it's always the side with less moles of gas, because remember, if you think back to year 11 with our gas laws, it doesn't matter what gas it is, as long as you have the same number of moles, it's going to be the same volume, right? So that's why you want to decrease the volume of the gas to decrease that pressure a little bit, okay? It's going to shift to the side with less moles of gas. And the kind of opposite is true as well. So if we have less pressure in the system or an increase in volume, so there's something like less pressure in the system, what's going to happen is you're going to shift to the side with more moles of gas, because you want to produce more gas to bring the pressure up again, right? So it works in the opposite as well, okay? So that's sort of temperature, partial pressure, and total pressure. In the next few examples, we'll talk about some of the other different factors as well, right? But just to quickly summarize, with temperature, you always want to write out whether it's an endothermic or exothermic reaction. So the delta H generally tells you whether it's endothermic or exothermic for the forward reaction. So you just write it out, write heat as like a product of reactant, because it's exothermic, the heat is a product. And what happens is if you increase the temperature, it's like essentially increasing this amount of heat here, right? So if we increase this amount of heat here, that's too much, so you want to shift it to the other side, or you want to shift it to the left to minimize some of this heat increase, okay? And then temperature, if you decrease temperature, it's the opposite, so you want to bring the temperature up again, so you're going to favor the forward reaction because it's exothermic. You want to produce some temperature to increase the temperature of the system again, right? Partial pressure is essentially increasing the amount of a particular species of gas in the reaction, right? Not increasing the total pressure of the whole system, just increase the amount of gas in a particular system. And if you increase the amount, that's too much, doesn't like it, the equilibrium is going to shift to the other side, right? So it's going to shift to the right in this case to minimize some of that gas increase by taking the CO2, taking the water, and then converting it to carbonic acid. And that's the opposite if you decrease the partial pressure. So if you decrease the partial pressure of CO2, the equilibrium is going to shift to the left because it wants to increase the amount of CO2, okay? And then finally with total pressure, if you change the total pressure, so if you increase the total pressure, for example, the equilibrium will shift to the side with less moles of gas because it wants to decrease that total pressure a bit, and it decreases that by having less gas present, okay? And that's the opposite. If you decrease the total pressure, the equilibrium is going to shift to the side with more moles of gas because it wants to bring that pressure up again, okay? Now, if we think about how this sort of applies to soft drinks, right? Because we said this CO2 is a carbonic acid example, really common in soft drink, and it definitely is common in soft drink. We just don't know it. Now, I'm just going to rewrite this equation for the third time, right? Again, right, and that's going to form in equilibrium H2CO3 like so, okay? And that's aqueous, liquid, gas, and then liquid, right? Now, the sort of good stuff that you taste in the soft drink is carbonic acid, right? So this is sort of the good stuff that you taste in the soft drink, and you want as much carbonic acid as possible, right? Now, let's think about how temperature and pressure affect soft drinks, right? So if, say for example, you increase the temperature, right? If you increase the temperature, what essentially happens to your soft drink? Well, you tell me, right? What happens when you put your soft drink out in the sun? Well, it doesn't taste that good, does it, right? The soft drink goes flat, right? And the soft drink goes flat, and we've experienced that before, right? If you leave it out on the kitchen table, forget to put it in the freezer, soft drink goes flat, right? And so the reason why that occurs is because if we increase the temperature, well, in this reaction, we said that the forward reaction is exothermic, right? So it produces heat. Well, if we increase the temperature like so, right? We said we increase the temperature, it's essentially like increasing the heat. Well, there's too much of it. So what does the equilibrium want to do? Well, it wants to shift to the left, okay? So this is the first thing that happens, you increase the temperature. And so what happens is the equilibrium shifts to the left, right? That's the second thing that happens. And then what happens when you shift it to the left is you get more water, but more importantly, more CO2 being produced, right? So more CO2 is being produced. So you get an increasing amount of that. That's the third thing that happens, right? You get an increasing amount of CO2. And what's going to happen there? If you produce CO2, that's going to get blown off into the environment, right? So that's why if you leave your Coke out in the sun, right, your carbonic acid, the heat's increasing, so your carbonic acid is going to get broken down into water and carbon dioxide, and then that carbon dioxide is going to get released, and that's why your soft drink goes flat, okay? And it's because right? It's because our CO2 is being released, right? CO2 is being released like so, okay? And that's why, again, the opposite occurs. The soft drink tastes a lot better when you put it into the fridge, because what you're doing is you're decreasing the temperature, right? And by decreasing the temperature, you're encouraging the water and the carbon dioxide to convert into the carbonic acid, okay? So that's why it works in reverse as well, yeah? Now, the second thing, right, that can affect the soft drink is if we decrease the pressure, right? And this is the total pressure, right? So we just decreasing the total pressure of the system. Well, let's think about what happens. What happens when you take the lid off the soft drink? Lots of gas gets released. And what happens if you keep the lid off? Well, then it goes flat, right? And the reason why is because you've decreased the pressure. In those Coke cans or in those Coke bottles, it's pressurized, right? So it's not your atmospheric pressure. It's more than that. They pump extra gas in to increase the pressure to make it taste more fresh. And why does that? Well, it's because if you decrease the pressure, well, again, we know that the soft drink goes flat as well. Okay, we know the soft drink goes flat, and the reason is because let's think about our rule before. If you decrease the total pressure, the equilibrium will shift to the side with more moles of gas, because you've decreased the pressure. It wants to increase that pressure back up again, so it's going to shift to the side with more moles of gas, right? Equilibrium shift to side with more moles of gas. And i.e. in this example, that would be to the left, right? It's going to shift to the left because it wants to produce, right? To produce CO2, right? It wants to increase the amount of CO2 to offset the pressure decrease, okay? To offset the pressure decrease. So essentially what's happening is we've decreased the pressure, right? Not good, right? Big soft drink goes flat, and the reason is because the equilibrium is shifting this to the side with more moles of gas, right? Which is the left-hand side because the CO2 here, right? In order to try and bring that pressure back up again. And if you keep keeping the lid off, it's going to keep producing that CO2 and releasing that CO2 to try and increase the temperature again. And so that's why your soft drink goes flat, okay?